Ionic compounds are always formed between what two types of elements? They are metals and nonmetals. Remember that you can identify them by just looking at the periodic table. That one doesn't have the zigzag line, but this one does. So remember that everything to the left is a metal, everything to the right is a nonmetal. So you're looking at things where you're going to have elements on opposite sides of that zigzag line. In the steps, you assign the element a charge. What do you have to use on the periodic table to figure out what the charge of the metals and the nonmetals will be? What are you looking at on the periodic table? You're looking at the group number. That is at the top of the column. It is the number in front of the capital A for the main group elements. So again, not on that periodic table, but on this periodic table, you see that you have 1A, 2A, 3A, 4, 5, 6, 7, and 8A. That number tells you the number of valence electrons. So if you're talking about the metal, that number is its positive charge. So the metal's always going to have a positive charge by that group number. The nonmetal is always going to have a negative charge. So if you take the group number minus 8, that will tell you the charge for the nonmetal. So one of the ones that we looked at that's a good slide to sort of use is this one. Because this slide shows you the group numbers, see the group numbers listed across the top. See the two red boxed groups? They're called the main group elements. So they're the first two columns and the last 6 columns. With those, that group number tells you the number of valence electrons. With metals, that is the ones that are in blue. Notice that the metals always have a positive charge. Metals always lose those electrons. The nonmetals, the ones over in yellow, over on the far right side, they're going to gain electrons. So if you take 8 minus the group number, that will tell you that charge. So nitrogen has 5 valence electrons. 8 minus 5 tells you it's a negative 3. Oxygen has 6, is in group 6. 6 minus 8 gives you the negative 2. Okay, that's how many electrons it's going to gain in order to make that 8. So just remember with the nonmetals, it's always 8 is the goal. So whatever electrons they have to gain, that's going to be their negative charge. So the ones that are listed, first 2 rows, and then over on the 6 far right. So in this one, what element do you always write first? The metal, okay? So the metal is always going to get listed first. So metal, then you'll put the nonmetal in. When you say the name, what do you use? The whole name of the metal. How much of the nonmetal? Just the first part, and at the end you add IDE. So based on that, let's do these. These are the ones people usually can flip through pretty quickly. K2S would be what's potassium, whole name of the metal, first part of the nonmetal, sulf, plus IDE, potassium sulfide. Second one, Li3P, lithium phosphide, whole name of the metal, lithium. First part of phosphorus is phos, and then IDE. BeF2, Beryllium fluoride. Whole name of the metal. And then the last one, calcium nitride. Ca3N2, whole name of the metal, calcium. First part of nitrogen is NITR, niter, and then IDE. So that's going from the formula to the name, very straightforward, use the same exact process every time. When you're going from the name to the formula, here you have to figure out what the ratio is based on the charge. So for this one, for for sodium nitride, just list the elements. So sodium is Na, nitrogen is N. Okay? Then you need to figure out what's the charge on each one. Sodium's in group 1, so we know it's A +1. It's in group 1A. +1 charge. Metals are always positive, so the group number tells you the charge. Nitrogen is going to be a -3. So we have a +1 and a -3. The ratio that they exist in will allow the positive and negative charges to balance. So to figure that out, you just take the charges and you do what? Swap them. The charge on the metal tells you the number of nonmetals. The charge on the nonmetal tells you the number of metal atoms. So it will be Na3N. The charge on the nitrogen tells you how many sodium. The charge on the sodium tells you how many nitrogen. If you can simplify it, make sure that you simplify it, right? So if you got like a 2 and 2, you would just simplify it to just a 1 and 1. But this one you can't simplify anymore. Calcium phosphide. So you just write down the symbol. So calcium is Ca. Phosphorus is P. Calcium's charge +2. Phosphorus's charge -3. Everybody know how to figure out those charges. Don't have to memorize them. You just have to remember that you look at the periodic table. The group number is going to give you the charge for the metal. Calcium's in group 2A, charge is a +2. Phosphorus is in group 5. 5 minus 8 is -3. So I always think with the nonmetals, like how many electrons do I gain to make 8? So since I have 5, I've got to gain 3, giving me a -3 charge. Remember, electrons are negatively charged. So now to figure out the formula, do the swap. Calcium gets a 3, phosphorus gets a 2. Charge on the calcium tells you the number of phosphorus. Charge on the phosphorus tells you the number of calcium atoms. Do these two. See if you can do them. Just follow exact same. Okay, lithium oxide. Lithium is Li. Oxide is O. Charge on the lithium, +1. Charge on the oxygen, -2, or 2-, doesn't matter if you put the minus or in front of or behind. 2-, -2, same thing, just means 2 negatives. Okay, then all you do is swap. Li2O. Simplest ratio already there, so you just leave it as it is. Magnesium iodide. Magnesium is Mg. Iodide is I. So it's iodine. Charge on a magnesium, +2. Charge on an iodine, -1. It's in group 7. It's going to gain 1 electron to make 8. Okay, so always double check where it is at the top. Check the group number. Nonmetals gain electrons to make 8, so it's in the 7. So it's going to gain 1. That gives it a negative charge. Then swap. Mgi2. Charge on the iodine tells you that there's only 1. There, shrink it down so you can see it. Charge on the iodine, -1, tells you 1 magnesium. Charge on the magnesium, +2, tells you that there's 2 iodines. So the other part that we went to is on the back side. So transition metals and polyatomics, these were the 2 exceptions to the rule. Okay? With all other ionic, just follow exactly the way we did them on the previous page. But when you have transition metals are the metals that you find in this area. So the ones that have a B, notice that these don't have a capital A. There's a B at the top. Their group numbers are like 3B, 4B, 5B going across. What is sort of different about them is they don't automatically lose a certain number of electrons. They can exist with a variation or a variety of different types of charges, always positive, but there's just 3 that I want you to know. And the reason is because we will talk about them again. So one of them is iron. So iron can exist as Fe plus 2, or iron can exist as Fe plus 3. Chromium, same thing. Chromium can exist as Cr plus 2 or Cr plus 3. Copper, the last one, can exist as a plus 1 or a plus 2. Plus 2, 2 plus, either way. So because of their electron arrangement, they can lose more than one group of electrons in order to create this stable ionic compound. So the problem with this is, if we look at this one, so if you were just to name Cr2s3 according to the way that we numbered in that we named on the front page, what would you call that? Whole name of the metal, so that would be chromium. First part of the nonmetal plus IDE, sulfide. Okay, so you just want to write, okay, it was chromium sulfide because it's an ionic compound. The problem comes into play, which one is it? Okay, which charge does that chromium have? Which is why you have to add the Roman numerals. The Roman numeral goes in between the metal and the nonmetal. The Roman numeral tells you the charge on the metal. So you have to work backwards with these, okay? So Cr2s3, the number, what did we do in the previous one? To figure out the formula, we used those charges. So you're really doing like a reverse swap. So take the charge, the number of chromiums tells you the charge on the sulfur. So that means that this sulfur has a what? It'll be a -2. Remember, the nonmetals are always negative. That means that the charge on the chromium is +3. I used the formula to figure out the charge. Remember, we did the charge to figure out the formula. So this is really just like a reverse swap. So we're just taking the number of metals, tells you the charge on the nonmetal. So you can double check this because sulfur is in group what? Group 6. So would it have a -2 charge? To make 8? Yes. Okay. So you can check the nonmetal because it's going to have a defined negative charge. So see that the sulfur has that -2. That means that that chromium has a +3. So to indicate that, you put III, or a Roman numeral 3 between, and that's telling you the charge on the chromium. So the next one, FeF3 would be not chlor. That's fluoride, iron fluoride. So just like any of the other ionic naming, you would do it that way. To figure out the charge on the iron, do the reverse swap from the formula. So that means that the charge on the iron would be +3. The metal's always a positive. The charge on the fluorine would be -1. Does that fit? Is fluorine, what group is fluorine in? 7, so it would have a -1 charge because it's going to gain 1 electron. So you're just taking the formula and doing that reverse swap. Okay, so like just as a general sort of rule on this one, if you see XY, whatever the formula is, metal and a non-metal with a formula, and you need to figure out the charge, do a reverse swap. So the number of metal atoms tells you the charge on the non-metal. So this number down here would tell you the negative charge of the non-metal. The number at the non-metal would tell you the positive charge of the metal. So this one tells you that. Just like if I give you the name, you can figure out the formula by assigning charges and swapping, going the other direction. I would kind of call this a reverse swap. So copper 2 chloride, how do you figure that out? What's the symbols? Cu, Cl. Okay, so first thing, look at the elements, convert them to their symbols. If it's copper 2, what's the charge on the copper?
So does iron not have 3?
Oh, wait, it does have a 3. Sorry. Put 1, 2, 3. That plus 3 would put the Roman numeral 3 in between iron and fluoride. Sorry, I jumped ahead. So copper 2 chloride, the copper has what charge? It's a plus 2. The Roman numeral. You don't have to figure it out. The Roman numeral tells you the charge on the copper. And if you look at the periodic table, chlorine has a -1. It's in group 7. It'll always have a negative charge. So to figure out the ratio, charge on the metal tells you the number of nonmetals. The charge on the nonmetal tells you the number of metal. So the last one, iron 2 nitride. So first, what are the symbols? Fe and N. Iron 2 tells you the charge on the iron is +2. Look at the periodic table to figure out nitrogens. What's the charge on the nitrogen? -3. It's in group 5, means it's going to gain 3 to have its 8, -3. So the ratio, Fe3N2. Okay, we'll do some more practicing with these. We're going to add in the next ones. But the last one that gives everybody a challenge are the polyatomic ions. Polyatomic ions are groups of nonmetals that collectively have a charge. Most of them are a nonmetal with a bunch of oxygens. Okay? And mostly their names come from that nonmetal. So when you have NO3, that's a nitrate. So it's like it's got a nitrogen, and then with all those oxygens makes it the nitrate. So SO4, 2- is a sulfate because it's got a sulfur in it with all those oxygens. ClO3- is the chlorate. So you see how those names, the names for most of them kind of fit. Nitrogen's the nitrate, sulfur is the sulfate, chlorine has the chlorate, and then PO4, 3-, that is the phosphate. It's the phosphorus with all those oxygens. It's a phosphate. 2- -2, either way you write it. CO3, 2- is a carbonate because it's got a carbon. Okay, so those ones, when going through in the naming, there's 2 oddballs. This one we talk about because we're going to talk about OH negative quite a bit. The OH negative is a hydroxide. So that one's not one of the 8s, but it's a hydroxide. It's characteristic of a base. So we use sodium hydroxide in lab. So if you've ever used Drano, that's a hydroxide. Lye is a hydroxide. And then the other one is the only positive polyatomic you have to know. So those are the 7. They're listed in your book. You need to know the names, the formula, and the charge so that you can be able to name them or write their formula. So again, you do get a card. You get an index card. I'll give it to you. What's today? I'll give it to you on Thursday so you can start figuring out what you want to keep. But with that one, this one is called the Ammonium Ion. And it is the only positively charged polyatomic. So with this one, this ammonium ion, you'll actually put it first in the formula because it's like a metal. Since it has a positive charge, it sort of sits at the front of the name. With polyatomics, you just use the name of the polyatomic. So if you see a polyatomic in the formula, then it'll just have nitrate or sulfate or phosphate. So you won't have any IDE additions to it. You don't have to change it. You just use the name of the polyatomic. So we'll do again, because these ones seem a little bit easier because you don't have to figure out any formulas. All you got to do is the name. You always use the whole name of the first sample. And then the second one, if it's a polyatomic, you just use the name of the polyatomic.
What did you say the CO3 was?
That's the carbonate. So it's like carbon with all those oxygens is the carbonate. Phosphorus with all those oxygens is a phosphate. Nitrate, sulfate, and then chlorate. So K2SO4, what would you call that? Potassium? Sulfate. You just use the name of the polyatomic. Okay, so the SO4 as a group is the sulfate. NH4Br. Ammonium bromide. You always just use the name of the polyatomic, so you don't change it at all. Don't worry about adding. You don't have to name the nitrogen and hydrogens there. You just call it ammonium. So BeOH2. Hydroxide. Al2CO3. Carbonate. So aluminum carbonate. So CO3 is the carbonate. So if you're given the name and you have to figure out the formula, you do have to use those charges to be able to figure out the ratio. And so that's where having the name, the formula, and the charge with those. So the first one, so sodium is Na. Nitrate is NO3 and has a negative charge. What's the charge on a sodium? +1. It's in group 1A, so it has a positive 1 charge. So in this one, it's 1 and 1. So the formula is just the way it's written. So it's already kind of like sodium chloride. It's already 1 positive, 1 negative, so you don't have to do any swapping. It's just NaNO3. Calcium phosphate. Calcium is Ca. The phosphate is PO4, and it's a 3- or a -3. What's the charge on the calcium? +2. Trying to write that a little better. There. So swap them. So how many calcium? 3. What do I have to do if I have 2 phosphates? Use parentheses. PO4, 2. Ca3, PO4, 2, with the parentheses around that phosphate group. So remember when we balanced equations, you saw groups that were in parentheses? If you go back and look at that balancing equation sheet, they're all polyatomic ions. Okay, you'll see that it was things like CO3, SO4, NO3. That's when you put the parentheses around because that acts like one group. Rather than separating, it's always kept together, and that's why you need the parentheses. So lithium sulfate, lithium is Li, sulfate is SO4 and has a -2 or 2-. Lithium is its charge +1. So then just swap them. How many lithiums do you have? So it would be Li2, and how many sulfates? Just 1. So you don't have to use parentheses. If there's only one of them, you can just list it. So LiSO4, Li2SO4. All right, so the last one, magnesium chlorate. Magnesium is Mg, and chlorate is ClO3, the negative. So magnesium is +2. So you end up having to do what? So magnesium, you'll only have 1. ClO3, you'll have to have 2. The charge on the magnesium tells you how many chlorates. Charge on the chlorate tells you how many magnesium. If you have a polyatomic with more than 1, put the parentheses around it. Just put the number outside. So like I said, we'll continue doing more practices with those. That's why I wanted to give that to you as a handout so you didn't have to worry about trying to write all of it down. You can just go ahead and fill it in. I'll also post this as well in Moodle. This is a really good chart to use to go through and list your charges of the metals and nonmetals. But remember, you really don't have to memorize this. You just have to remember how to figure out the charge. You just have to remember that metals, the charge, the group number tells you its positive charge. With nonmetals, whatever you have to add to make 8, that tells you what their negative charge is. So you may add this into your list, and then those are the 3 transition metals that you need to be familiar with: chromium, iron, and copper. Just those 3. You don't have to worry about the gold or the lead or the tin, the other ones that are listed there. Just those ones will be fine. This is that list. So this comes from a table in your book in chapter 3. So this is another one that you can refer to. All right. So ionic compounds have a lot of importance in the body, but in fact, when they're put in water, most ionic compounds separate. So instead of, if you eat salt, sodium chloride, they don't stay together. They can dissolve in water and they actually float separately. And so when you talk about ions, you rarely talk about the metal and the non-metal ions together. You talk about them individually. So in the body, there's major positively charged ions called cations. Remember that that's just an atom with a positive charge. They're your metals. And these are really the big ones. We'll talk a little more about the anions as well, but we're going to save those more for some of the acid-base balance when we get into acids and bases, which is like chapter 9. But with these, sodium, potassium, calcium ions, iron, 4 big ones, they have, rather than building large structures, these have more of a functional importance. For the body. Sodium helps to regulate water balance. Where sodium is, water hangs out too. So if you have a lot of sodium, you're going to have a lot of water that has to be in that area. So good example, if you watched the Super Bowl on Sunday, and so you ended up having the chips and the dips, and maybe you had like some fries and you had some salt on top of your salt for the evening. And so you may have noticed like throughout the evening, you might start feeling more and more thirsty. If you ingest large amounts of salt, water needs to hang out with the salt. Sodium is a very important water balancer. So where there's a lot of sodium, you're going to have a lot of water. For me, I get this sensation when I eat Chinese food because Chinese food has MSG, which is monosodium glutamate. So it's a salt, has sodium in it. And so as soon as I finish eating, I'm always like, oh, I'm really thirsty. Like I'll just find that I'm like drinking a whole lot after eating that. So when there's a high amount of sodium in the blood, that is going to pull more water, making you thirstier. But all of that, if you increase sodium and water volume in your blood vessels, that'll increase your blood pressure. So instead of keeping that extra volume in the blood, you shift that fluid into tissues. And so what do you start to notice about like your fingers, your rings, your ankles? You'll notice some minor swelling. Okay? So if you increase sodium intake, that will increase water retention. And that can lead to minor edema. So you'll notice like your rings are tight. Or maybe when you take your socks off, you notice that your ankles look skinnier than your legs. That's just because they've been squeezing the skin, keeping it from collecting. You can get minor edema. So how do you get rid of this excess sodium in water? What organ does that? The kidneys. And for most people, over the course of 24 hours, your kidneys just excrete the excess. Okay, so you excrete the excess salt and the excess water goes along with it. What about people that have high blood pressure? What is this going to do? If you increase sodium intake, it's going to increase water retention. And what's that going to do to your blood pressure? Make it go up. And so what does the doctor tell somebody that has hypertension or high blood pressure? Yeah, you want to limit your salt. Because wherever salt is, water's going to hang out too. Increasing sodium intake increases water retention and puts more pressure on those vessels. So that can be a challenge in balancing. Second one, potassium. Potassium and sodium are really important with nerve impulses, transmitting and stimulating muscles and glands. But you notice more of an effect when potassium levels are too low or too high. Low potassium levels, so this is muscle contraction, which is stimulated by nerves. If your potassium levels are low, you can cause spastic contraction of muscles. So this always seems to happen in the middle of the night. And what do you end up with? A cramp. Okay, so you wake up in the middle of the night, you're like, and you're like staggering around the room, trying to stretch it out, trying to get it to stop. That can be because of lower than normal potassium levels. So what did your mother always tell you if you had leg cramps? Eat a banana. So look at where one of your sources. A source of potassium is a banana. So that is part of that rationale or reason. Low potassium levels can cause muscle cramps. Extremely low potassium levels can actually end up affecting another muscle in your body, the heart. So it can cause a weaker than normal contraction. This is why if you have patients that have been in the hospital, they're really sick, oftentimes they give them potassium as a supplemental into their IV to try and strengthen heart contraction. Low potassium can cause just minimal leg cramp, but worst case scenario can actually weaken the contraction of the heart. So things like water balance, muscle contraction, nerve impulses. Calcium, the one thing this is one that most everybody is familiar with. When you think of calcium, it's important for strong bones. Strong bones. Also important during childhood because of development of teeth enamel. Okay, so the enamel that covers on your teeth, made of calcium as well. Last one. Well, if you don't get enough calcium, then as you get older, you run the risk of osteoporosis. Okay, so you can see with these ions, not having regulated levels of these ions can end up leading to imbalances. So the strength of bones and teeth, without it, low calcium, osteoporosis is a risk. Last one, iron, the +2. So iron 2 ions, these are really used to produce a specific type of cell. This cell helps to carry oxygen through the blood. They are the red blood cells. Contained within the red blood cell is really one major protein called hemoglobin, and that contains these iron atoms, or their ions. You need this iron to be able to pull oxygen into the blood. So if you don't get enough dietary iron, you can develop what? And it's called iron deficiency anemia. Iron deficiency anemia leads to less oxygen in the blood. The person tends to be pale, stand up too fast, you get kind of dizzy, you get winded really easily because you don't have as much oxygen in the blood as your muscles need to be able to power contraction. Just wanted to go through some of those ions and give you examples of what happens if they're not regulated, or you're not intaking them enough, or if you're intaking too much. Okay, excessive amounts of ions, not enough of these ions, and you can end up having physiological changes in how the body functions. All right, second type of bonding. So we're talking about things like sodium and chlorine, right? So sodium and chlorine, remember that they are, sodium's over here, chlorine's over here. Metals and nonmetals on opposite sides of the zigzag line. But there are compounds that are formed where it's not that we have almost no electrons in the valence shell and almost a full set. What about when you have two hydrogens? So if I have a hydrogen and a hydrogen. So a hydrogen needs how many to be stable? So hydrogen's in group 1. It has one valence electron. So what does it need to be stable? Go across, find the noble gas that it matches. The noble gas is helium, which has just 2. So remember that first energy level only holds 2 electrons. So that hydrogen needs, it has 1 electron and it needs 1 electron. But what about the one on the opposite side? Exact same, yeah? So this has 1 electron and also needs 1 electron. In order to be like helium, to be stable like a noble gas, hydrogen just needs to have 2 electrons in its outer shell, or valence electrons, to be stable. So can the blue hydrogen pull an electron from the red one? Can the red one pull an electron from the blue one? They have the same attraction because they have very similar numbers of valence electrons. So they can't transfer. Hydrogens are not going to lose that electron because they want it the same strength. The only way that they can form a stable arrangement is to share. So rather than having ions formed, you have a covalent bond where you have sharing of electrons. That means that the hydrogen's electrons are positioned between the 2 hydrogens. This left hydrogen, therefore, has 2 electrons some of the time, about half. The red one, the opposite, has 2 electrons as well, part of the time. That creates stability. So by sharing a pair of electrons, you make a covalent bond. I always think of covalent bonds as being like links. Ionic is just like you just transferring and making these charges. But with these, you're really sharing these two electrons to form a link between the two. You'll sometimes see this drawn like this with a dash. So remember that a dash means one pair of electrons is being shared between the atoms that are between on either side of the line. This is why you always see H2. Okay, if hydrogen is found like hydrogen gas, it's H2. It doesn't exist as just individual H atoms because it's too reactive, but it can exist as H2. This is also why you have Cl2. Chlorine gas doesn't exist as a chlorine atom. Chlorine gas exists as Cl2. You can see in this one, so here's the initial, 2 chlorine atoms. When you count, they're in group 7. So notice that you've got 1, 2, 3, 4, 5, 6, 7 around each chlorine. They colored the one that's not paired in red. So you see that they're kind of like on opposite sides. So the left chlorine, its little red dot is on the right side. The right chlorine, its little dot's over on the left side. So neither chlorine can pull electrons from the other because they each want one electron, and they have a really strong attraction for an electron because they're almost full. So they just slide over closer so that their orbitals can overlap, so that that one pair of electrons can be shared between them. So it allows this chlorine to behave like it's a noble gas. It's going to behave like it's argon because it adds, by sharing, it's as if it has its 8. Same thing with this chlorine. So it also has its 8. So the line that you see between the two chlorines is a single covalent bond. Now, just note, these electrons, the 6 electrons that belong to the individual chlorines, they are not in the middle. They do not get shared. They belong to each chlorine. Okay? So in that overlapping, not all the electrons go back and forth, just the shared ones. So the shared pair are spanned between, but any other electrons do not get put in that space between. They call them sometimes lone electrons or non-bonding. I kind of like non-bonding because it makes me think like those ones are just off by themselves. Those ones just belong to one atom. They don't participate in a covalent bond. So this is why you'll see all the halogens. So chlorine is Cl2, fluorine is F2, bromine is Br2, iodine is I2. So they always exist as pairs. They're all group 7, so they all form one. They call these diatomic. Diatomic elements, because if you find them individually, if you find hydrogen gas in nature, it's going to be H2. Chlorine gas in nature is Cl2 because it's going to automatically have a single covalent bond between 2 of the same elements or same atoms to form the molecule. So, if you have different elements, steps that you do, and this is really like step 2. Step 1, and you probably don't have to keep doing it this way, but I will just show you sort of in all of the steps on how to figure out a covalent molecule. Most of the time you get used to it and you'll just automatically start to know how many bonds each atom has to have. But the first thing that I always do is I list the atoms in the molecule, list the atoms in the formula, list how many valence electrons, and then figure out how many bonds. For all the nonmetals except for hydrogen, they always need to have a total of how many valence electrons? What's the rule? So for carbon and nitrogen and oxygen and sulfur, chlorine, bromine, they always want to have how many in their outer shell? 8. So the rule is always 8. Hydrogen's the only oddball, right? Because hydrogen has 1 electron and it needs 2 to be stable, okay? So in this first one, so with CH4, I have carbon. How many valence electrons will carbon have? You can tell by its group at the top of the column. It's got 4. Okay, it's in group 4A. That means that it needs 4 bonds. So the number of electrons and the number of bonds is going to equal 8. 4 electrons for carbon, 4 bonds are needed. Hydrogen has just 1. But it's the oddball because it needs how many bonds? Just 1. So second step is you're going to start with the atom that needs the most bonds. So all you do is look through which one needs the most. Carbon. So I'm going to start off and put carbon first. Carbon's got 4 electrons. Sorry, that little dot's just my pen. It just always looks like an extra dot. All right, 4 valence electrons, and I split them out. So I put 1 above, 1 to the left, 1 right, 1 below. So I need to form 4 bonds, but you can see you've got 4 hydrogens. So it makes sense that you're just going to put 1 above, 1 below, 1 to the left, 1 to the right. Hydrogen here, pairing, hydrogen here, hydrogen here, hydrogen here. Does every hydrogen have 2 electrons now? Okay, so this hydrogen can act like it's helium. This one can be like helium. This one has 2. This one has 2. So by sharing, they all have 2. And then what about carbon? How many does it have? Carbon now has a total of 8. It's 4 plus 1 from each of the hydrogens. You may see this drawn with the dashes. Carbon in the middle, dash up, down, left, and right, 1 hydrogen on each one. You've used all 8 of your electrons, and all of them have a full valence shell. So what about water? So you go through, do the same thing. Hydrogens, 1 electron, 1 electron. Oxygen has, what's its group? 6. So hydrogen needs 1 bond, 1 bond. Oxygen needs, to make 8, 2. So other than hydrogen, it's just how many bonds does it need to have that 8? Start with the oxygen, put it down 1, 2, 3, 4, 5, 6. Doesn't matter how, you're going to have 2 sides that'll have pairs and 2 sides that'll be single. So I usually just start and go 1, 2, 3, 4, and then start pairing, doubling them up. Put them a maximum number of 2 at the top or 2 on the left or right or below. And you see that there's like 2 empty spots. Okay, so you can see the left and below, they don't have a pair. And so that shows you where to put the hydrogens. Put a hydrogen here, put a hydrogen here. That's going to give, each hydrogen is going to have that pair shared. And it's going to give oxygen, it's 6 plus the shared 2 gives it a total of 8. Now, when you draw this as a Lewis dot structure with the dashes, keep those non-bonding electrons because they do take up space. It would not be wrong if you drew this, like when you get done, it looks like this. It'll be all right. All you have to make sure is that you have an oxygen with 2 pairs of non-bonding electrons somewhere. They could be on the side, they could be above, they could be this side. Just 2 pairs of non-bonding electrons and then a single bond to 2 hydrogens. So as long as you have 2 hydrogens connected, these are not stuck. These molecules roll around. So whether you put it like this or you put it like that or you make it look like they're straight out, that's all correct. Okay, so the position of those hydrogens does not matter. You can stick them up and down, you can stick them left and right, or you can make them look like an L. We're going to talk about shape and some of the sort of like appropriate ways to draw them, but any way that you drew it would be fine. Just so long as you have oxygen in the middle and you have the hydrogens bonded, single bonds to them. NH3 is ammonia. So do this one. Remember, you figure out the number of electrons by looking at the group number and the number of bonds it would need in order to have a total of 8. Except for hydrogen, that's the oddball. It always has 1 electron and only forms 1 bond. Notice all of these ones have a total of 8 electrons. It's pretty simple. It's a simple molecule with only 1 in the center and something around the outside. Start with nitrogen. Nitrogen has 5. See how it leaves 3 empty spaces to the left, right, and below. Just put a hydrogen in each of those spots, pairing. Gives nitrogen its 8, gives each hydrogen its 2. Wouldn't matter where you put those non-bonding electrons, as long as they're on one side of the nitrogen. They could be at the bottom or on the left or right. But there are occasions where you're not going to have enough electrons to give them all single bonds. So another diatomic element is oxygen. Nitrogen is the last of the diatomic elements. So we went through like hydrogen, chlorine, fluorine, bromine, iodine, oxygen, and nitrogen. The oxygen in the room always exists as O2. So if you give somebody oxygen, you don't say give them O, you always say give them O2. Okay, look at their O2 levels, like saturation levels. Same thing with nitrogen. 78% of the air is nitrogen. It exists as N2. So do the exact same thing. Oxygen has how many electrons? It's in group 6A, 6 electrons. So that means it's going to form 2 bonds. So if you start off and you put 1 oxygen down, 1, 2, 3, 4, 5, 6. And you go to add the other oxygen. When you do the pairing, 1, 2, 3, 4, 5, 6, pair them that way. Do you notice that, okay, I've got the pair in between, but can you see that there is a missing one here and a missing one here? But I've used all of my electrons. I only have 12, so that all 12 are down. If you get to this, if you have unpaired electrons, that's going to tell you that you've got to make a double bond. So you're going to take and move this electron in between the 2 oxygens and this electron. So you're going to make 2 pairs of electrons that get shared. The non-bonding electrons stay where they are. I'll use a red because you can see it a little better. But the paired electrons end up in between. So whatever's between the two oxygens, those are the ones that are shared. The ones that are out just around single oxygens are not shared. But can you see that now the purple oxygen has 8? The red oxygen has 8 when you do the counts. Total number of electrons here, 8. Total number of electrons here, 8. That's a double bond. So you will see this drawn with 2 dashes. So remember, every dash represents a pair of electrons. But you have to share 2 in order to create that stability. So do nitrogen. Nitrogen is in group what? So it's 5 electrons. 5 electrons. That means that they each have to have 3 bonds. So you can see how that's going to create a problem. I've only got 10 electrons, and I'm going to have to share until I end up with 8 on both. So if you start off with the nitrogen, 1, 2, 3, 4, 5. Add the other nitrogen, 1, 2, 3, 4, 5. So you can pair them off. Can you see that you've used all 10 and there's unpaired on either side? So then you just start forming multiple bonds. Move so that they're between by moving this into the middle. That forms a double bond. That's not going to be enough. You're going to have to take that other pair and move them into the middle as well. So you end up with a nitrogen with 6 total electrons between, to give each of them 8. They still have their non-bonding pairs, so there's 6 in the middle plus 2 non-bonding per nitrogen. That's a triple bond. Triple bonds, you don't see them all that much. Nitrogen gas is one of the few ones that you do see, and you would actually see 3 lines between them. Each one represents a pair of electrons. So work on these 3. We will do these 3 first thing when we pick up next time. A good page to look at to help you to see is this one. Okay? So this one shows really the main nonmetals and hydrogen that form covalent molecules. So we have hydrogen. Remember, 1 electron needs 1 bond. So hydrogen is only ever going to have 1 line sticking off. Hydrogen is never in the middle. Like hydrogen is never the center part of a molecule because it only ever forms a single bond. Same thing with the group 7s. So group 7s, all the halogens, fluorine, chlorine, bromine, and iodine, they have 7. They only make 1 bond, right? So they have 7 electrons, and so they're all going to need 1 bond. So you will, again, fluorine, chlorine, bromine, and iodine, you're always going to see that they'll just have a single pair of electrons when forming a bond to create stability. Oxygen needs 2 bonds because it's in group 6. 2 bonds in order to make 8. So oxygen can make 2 single bonds like we said with water, but oxygen can actually form a double bond like we did with the oxygen gas. So it's either going to be 2 separate or it could be a double bond with just 1 other atom. Nitrogen can do a couple of different variations because nitrogen has 5 electrons. That means that it's going to need 3 bonds. Well, it can do any combination of 3 bonds. It could do 3 single bonds, like the top one, or it could do a double bond in a single bond, like the middle one, or it could do a triple bond, like what nitrogen gas does. Any combination, as long as it shares 3 pairs of electrons, with other atoms to create its stability. Carbon, though, creates the most diverse bond types and arrangements because carbon has 4 valence electrons and it needs 4 bonds. So carbon can do 4 single bonds. It could do a double bond and 2 single bonds. It could do 2 double bonds. It could even do a triple bond and a single bond. Do you notice any combination of 4 sticks coming off of the carbon is going to give it its total of 8. This is the basis of organic chemistry. Organic chemistry is the study of carbon-containing molecules. And the reason why it's its own chemistry division is because of how many different things carbon can do. All these different types of bonding arrangements. Carbon makes long chains. Carbon can form ring structures. So it's really what we're going to talk about. All of chapter 4 is all about the carbon-containing molecules. But looking across, H, C, N, and O, what's significant about those? Those are what? They are the main elements. H, C, N, and O, Chan. That's your carbon, hydrogen, oxygen, nitrogen. 96% of the elements in the body, carbon, hydrogen, oxygen, and nitrogen. These are all of the big building blocks. Carbon, hydrogen, oxygen, and nitrogen are used to build structures like your carbohydrates, proteins, lipids, nucleic acids. There's a few other small minor elements thrown in there, but those are really the big ones. So when I think of covalent molecules, these are the structure molecules. These build big things, okay? They build long strands that then get calcium added to them to make them hard to form your bones. So we'll talk about those throughout the rest of the semester, but chapter 4, we're really going to focus on this. So one last thing before I go, and that's a good page though, or a good slide to look back on. So the last thing is the challenge in naming. So ionic, whole name of the metal, first part of the nonmetal, IDE, okay? Pretty straightforward. Your polyatomics, you gotta throw those in there. Transitional, you gotta use Roman numerals. Covalent though, they found that covalent, because it's sharing of electrons, you can have different variations of atoms. With ionic, you have transfer of electrons, and there's only one way you can make a neutral atom by taking electrons and passing them from a metal to a nonmetal. But here, we can have this, or we can have this. So we could have a carbon with 1 oxygen, or a carbon with 2 oxygens. You don't see that with ionic. With ionic, you have sodium chloride, 1 sodium, 1 chlorine. You don't see any other formula with sodium and chlorine. Here you can, because it's sharing of electrons. So what's the name of that first one? Carbon what? Think. It's when they talk about, so CO, poisoning is carbon monoxide. Close with the carbon oxide, so really very similar to ionic, but they put that mono in there. What is CO2? Carbon dioxide. So this is a great example of how you have to name covalent molecules. Because they can have a variety of bonding arrangements, you have to indicate number prefixes. Carbon monoxide means a carbon with 1 oxygen. Carbon dioxide means a carbon with 2 oxygens. Here's the list of them. Mono, if there's just 1. With the exception, if there's only 1 in the first element, you don't have to say mono. Okay, that's why CO is carbon monoxide, not monocarbon. So you only use in the second element of the formula. Di, 2, not such a hard one. Tri, 3, pretty familiar. Penta, hexa, hepta, 5, 6, and 7. Those were also pretty familiar because they sound like geometrical terms, like a pentagon, like a hexagon. So the only one that I find is the oddball is this one. Okay? So instead of a quad, they call it a tetra. Okay? So 4, if you have 4, it's a tetra. So based on that, tell me the name of NH3. whole name of the first element, first part of the second element plus IDE. That part's just like ionic. The only difference is add a number prefix. So that one would be nitrogen, tri. So first part of hydrogen plus IDE. Hydride. So the hydr, HIDR, first part of hydrogen, drop off the end, add IDE, just like we've been doing with ionic. Okay, what is water? Two hydrogens would be dihydrogen, whole name of the first element, monoxide. Thank God you don't have to call it that. Dihydrogen monoxide sounds much more chemical than water. Like NH3, its traditional name is ammonia, but nitrogen trihydride is its technical term or name. Dihydrogen monoxide. So what's H2O2? Dihydrogen, whole name of the first element, dioxide. Its common name is peroxide. So hydrogen peroxide that you put on a cut, it's clear, but it bubbles and foams. The only difference between water and peroxide is one oxygen. That's a big difference, though, in terms of its reactivity. You pour water on a cut and it just washes the cut. You pour peroxide on a cut and it's going to foam and oxidize and break down any microbes that might be in that cut. Big difference between them, so naming them is important. You need to use the number prefixes with covalent. What about CCl4? Carbon. Yeah. Carbon tetrachloride. Carbon tetrachloride used to be used as a fire extinguisher chemical. They found that if they sprayed it onto a fire, it's really dense, which means it's really heavy, and it covers the surface of the flame and blocks oxygen from being able to come in contact with the flame. So it's almost like smothers it. The only bad thing is if you heat carbon tetrachloride, it will break down and generate chlorine gas. So that was sort of a problem in a really hot fire, because all of the firemen would be like, because of the chlorine gas that would be generated. So they don't use that anymore, but that's what they used to use it for. So we got those top two. What about these last two? N2O5. N2. Dinitrogen. Pentoxide. So with penta, when you have an oxide, you'll drop the A off, so you'll just call it pentoxide. I've seen some that call it pentaoxide. N2O4 would be tetroxide. Very good. So this you see, except for the examples that we're going to go through, I'm not going to give you any ones to draw that are really large, drawn out types of ones. We'll do more of that in chapter 4, but if you just kind of go back over the ones we've drawn, like water, like ammonia, NH3, like CH4, work on CO2, the other ones, those other examples that I gave you. We'll do a little more naming, and we're also going to talk about how you can just easily look at a molecule and tell if it's ionic or covalent, so that you know how to do the naming. Okay?